I welcome you all to the data communication lecture annotation video for week 3 and lesson 1. In this lecture annotation video, we will discuss about data and signal. So let's begin. The first condition of data and signal is that of this topic is to be transmitted, data must be transformed to electromagnetic signal. To be transmitted, data must be transformed into electromagnetic signal, which is also called, when we need to transform the bits 1 or zeros to the electromagnetic signals. It is actually found in physical layer models that we have discussed previously. Now let's move on forward. What is data? Data is a bit of information, and the categories are analog and digital. The term analog data refers the information that is continuous. Digital data refers to the information that has discrete states. We will see in a bit what are analog and digital data, but to us, the continuous information is called analog data, and for discrete values are called discrete data, digital data. Analog data take on continuous values, digital data take on discrete values, and that is what I was talking about. Now let's move on forward. The topics to be discussed in this section are analog and digital data, analog and digital signals, periodic and non-periodic signals. We will get familiar with this really soon. So let's move forward. Here is the example of digital signal and analog signal. Now from here from the figure we can see digital signal has some really continuous values. So these continuous values are called analog values, which can only be represented by this kind of analog signals. And on the other hand, these discrete values, which have say for example 5 volt for 1 and 0 volt for 0, and this 10 volt for a value greater than 1, and so on. Some discrete values, not some in a continuous value, which can be represented by a digital signal. Analog signals can have an infinite number of values in a range, and digital signals can only have limited number of values. So this is the basic idea behind the analog and digital signal. So let's proceed on to the next topic, periodic and aperiodic signals. Both analog and digital signals can take of one of two forms. It is common in both digital and analog signals: periodic form and aperiodic form. In the periodic form, we see that a pattern within a measurable time frame called period and repeats that pattern over the subsequent identical periods. And in the aperiodic type of signals, signals changes without exhibiting a definite pattern or cycle that repeats over time. I'm repeating again. Signal changes without exhibiting a pattern or cycle that repeats over time is called aperiodic signals. In data communication, we commonly use periodic analog signals, and non-periodic digital signals. These two definitions are very important, so you must memorize it for your mid or quiz that I will take in the next week, I hope. So let's move on forward. Periodic analog signals. Periodic analog signals can be classified as simple or composite. A simple periodic analog signal is a sine wave which cannot be decomposed into simpler signals. A composite periodic analog signal is composed of multiple sine waves. We will see this firsthand in the figure, but we try to go along with the slide. So we are reading out the definitions in a bit. So in other words, a simple periodic analog signal is a sine wave which cannot be decomposed into more than one signal or simple signals. It is already the simplest form of a signal. So it is called simple periodic analog signal. On the other hand, a composite periodic analog signal is the type of signal that can be decomposed into multiple sine waves or multiple signals. So in this section, we will discuss about this kind of sine waves, wavelength, time and frequency domain, composite signals, and bandwidth. So let's move on forward and get on with these topics. This is the sine wave. Many of us is familiar with the sine waves. For a 0-degree value, it has a sine 0 degree will have a value of 0. For a sine of 90 degree, we have a value of 1, and so forth. For 180 degree, we again have a value of 0. And for 270 degree, we have a value of -1. And at 360 degree or 0 degree, at this point, we have a value of 0 degree. We have a value of 0 that is similar to the value of 0 degree, 180 degree, etc. and so on. Mathematically, we represent the sine wave as a function of time or t, where s is the instantaneous amplitude, that is the amplitude at the specific instance. A is the peak amplitude, that is here for the value 1 is the A, which is in the peak amplitude. F is the frequency, how soon this pattern repeats over itself, that is this starting from 0 going down to -1 and then reaching the 0. This is called the frequency. And sigma is the phase, that is the degree, which is where the data signal or wave is at this moment, and t is the time during which this period repeats, and pi, we all know, is a constant. Its value is around 3.14159 etc. So mathematically we define a wave like this. So let's move on forward. So I have already discussed the highest value of a wave is called peak amplitude. So here we have a high peak amplitude wave, and here we have a low peak amplitude wave. It's kind of self-explanatory, so I'm not going into details here and going and moving on forward. These are the formal definition of period and frequency, and we have to remember the connection between the period and frequency. These definitions are very important, and also their units and the representation or the symbol of frequency and periods. So take note of each of one of them, because you might find them in your quiz or mid. So to formally define the period, period refers to the amount of time in seconds a signal needs to complete one cycle. So when we have seen this sine wave, the total movement from this position and to this position and going through different values of this type of waves and information that are transmitted via the wave, this thing repeats. So this particular fraction of the wave is called a cycle. So that is what we define the time to go through this cycle. We define it as a period. And frequency refers to the number of periods in 1 second. So if we have, say for example, 10 periods in 1 second, then we have a time period is 1 by 10, that it takes only 1/10 of a second to complete a total cycle. And we have to remember that frequency and period are inverse of each other. So we need to be very careful about it. So let's move on forward. So here we see same amplitude and phase but different frequencies. So we know the amplitude is the peak or peak values in both directions. So when it is very frequent, that is time period is very small, we get this kind of cycles very frequent or very close to one another, and a frequency of less frequency we get this wave very distributed and elongated on the time axis. We represent any wave in forms of x and y axis. X and y axis, in the x axis we denote time, and in the y axis we denote the amplitude. So 12 period in 1 second, therefore frequency 12 is 12 hertz. That we have 12 cycles in every 1 second, and we have 6 cycles in every 1 second in a value of frequency 6 hertz. So I think you get that. It's kind of self-explanatory. And now here is the period and frequency units: milliseconds, microseconds, nanoseconds. I think you get the values of tens, the power of tens we are using here. So I'm moving on to the next slide. Here we see the first kind of example of mathematical nature. So we need to determine or find out the period of the sine wave having a frequency of 50 hertz. We already know the formula that time period and frequency are inverse of one another. So T here is the period, and F here is the frequency, and we know hertz, that is 50 hertz, which is also in terms or called per second. When it is divided, 50 hertz right down here, the power gets inverted, and we get 0.02 second as the time period, or simply put period, which is when we round it up, we get 20 milliseconds of the time period. If you understand that, you will have to find the time period of 1050 hertz and tell me in the Google Meet the answer of that time period. I hope you understand that. So let's move forward. Now here is the second bit of example. We are given here the time period in milliseconds. So we need to find out the frequency of this wave in kilohertz. So first we need to transform this millisecond into second, and then we convert or find out the frequency in hertz, and then we convert the hertz to kilohertz. So just to be sure, 1 hertz equals to 10 to the power minus 3 kilohertz. And that is what we are doing, that is transforming a unit to a superior unit. We divide it by a power of 10 to find out the answer. I hope you get the calculation. If you have any problem regarding the calculation, you should ask me in the Google Meet when we resume. So let's move on forward. So frequency is the rate of change with respect to time. Change in a short span of time means high frequency. Change over a long span of time means low frequency. These are, as usual, the conditions of frequency. But we have to be careful with these two conditions. It's kind of important to me. If a signal does not change at all, that is, if a Here we denote time and here we denote amplitude. You get the idea for the wave, but the wave itself is like this, and that is there is no change at all. Then the frequency is 0. And now if the change is instantaneous, the frequency is infinite. That is, we kind of see a very drastic change, and we know we only see a two line in both ways of the in both sides of the time, positive and negative. We don't see the wave or frequencies, but we see only solid lines in between them. Then the frequency is infinite, that we cannot measure that amount of frequency ever. So these 2 points are very important for your median quiz. So let's move forward. So I've already discussed about what is phase, and here it is being discussed in with some figures. It would be helpful for you. So I repeat the topic phase in here. So what I have here is frequency of a phase of 0 degrees, 90 degrees, and 180 degrees, with a cut between the time periods, 1/4 and half period, the starting of the phase. So in terms, a phase describes the position of the waveform relative to time 0. So when we start the time here for a sine wave, it starts at 0 degrees. When we shift the starting point to the right, that is to the value 1, that is to 90 degrees, the phase here we need not is 90 degrees. And when we shift the starting period to more right, that is towards 180 degree, we have a phase of 180 degrees. So in the following figure shows the same amplitude and frequency but different phases. That is what is being done in here. So I hope you get that. So let's move on forward. We measure phase by degrees, and we can also calculate it in radians. So let's move to that part. Sine wave is offset 1/6 cycle with respect to time 0. What is the phase in degrees and in radians? We know a complete cycle is 360 degree. Therefore, the complete cycle that is you're watching here, we start from 0 degree, move on to 90 degree, then move on to 180 degree, then to 270 degree, and then we move on to 360 degree. So 1/6 of a cycle is 1/6 into 360 degree, and we have the 60 degree as a phase in the degrees. And when we try to convert it to radian, we multiply the degree into 2 pi by 360 degree. So we get the result as pi by 3 radian. And when we get the constant out of here, that is the pi, we get 1.046 radian, which is the phase value in radians. I think you get that. So let's move on further. Wavelength is another characteristic of a signal traveling through a transmission medium. The wavelength depends on both the frequency and the medium. The wavelength is the distance a signal can travel in one period. That is, a signal is propagating like this, and the distance the wave travels in a period or in a cycle is called the wavelength of that particular signal. So wavelength depends on both the frequency and the medium. So we know that sound travels very slowly in the vacuum or in air, but it travels very fast when the medium is dense. So that is why the frequency and medium is the condition of the wavelength. And here is the formal distance or definition of how the wavelength travels. Wavelength is the distance a signal can travel in one period. And here we have a formula sort of how do we define a wavelength of light. By lambda, we define the wavelength. C is the constant, which is the speed of light, approximately 3 into 10 to the power 8 meter per second. And f is the frequency here. So you have to take a note of this formula. It would be useful later on. So here is the time domain and frequency domain, lots of sine wave. So I have already told you that we represent a sine wave in a xy graph, and we denote time in the x-axis and amplitude in the y-axis. But what happens if we replace time by frequency? For a particular wave, if the frequency remains fixed, then it has only one value, which has a peak amplitude of 5 volt. And here we have the same representation in with having time as the y-axis, with having the same characteristic of peak value of 5 volt. And in the frequency, and in the frequency representation, where frequency is represented in the x-axis, we get only one single straight line segment of value 5 volt, which represents the amplitude. So here is the topic that I was trying to enlighten you about. A complete sine wave is the time domain which can be represented by one single spike in the frequency domain. So what happens if we want to represent a frequency of 10, a frequency, say for example 10, f is equal to 10 hertz, and a peak value, say for example 10 volt. How do we represent this curve in frequency domain like this? You have to give me that answer when we resume in Google Meet. So take note and let's move forward. Here you are given how the frequency fares in the frequency domain. And it is kind of self-explanatory, because we have three distinct waves around here of different frequencies, and here three of them are represented in the frequency domain of the same three signals that we are seeing in the figure A. And now let's move forward. The composite signal. I have already told you about this kind of composite signal. That composite signal is we can break it down into more than one signal and have them described in a simple other signal. So that is what we are doing here. That is, we are defining two different signals right around here. A signal, the bigger one with higher amplitude right here, and the smaller one right here, like that. So when we gather these two signals, compose them into one, we get this kind of composite signal. So we do not need to worry about that thing at this moment. So let's move on forward, but you have to study this how this composite signals can be processed. I hope you get that. So let's move on forward. So here we get the decomposition of the composite periodic signals in time and frequency domains. What we see here is that in the time domain, it is kind of these are the decomposed signals, three separate signals, one of a very high amplitude, peak amplitude, peak value, another with medium peak value, and the signal will lowest peak value. But the signal with lowest peak value has the highest frequency, and the signal with highest peak value has the lowest frequency. And when we represent them in the frequency domain, it is kind of very easy to represent and represent them. So I hope you get that. Now let's move on forward. These are the figure shows in non-periodic composite signal, and when we represent them in the frequency domain, we get a kind of continuous values along the lines. There is no specific period or cycle in here, so they are called like this, the non-periodic composite signals. And in the frequency domain here is kind of interesting. We consider every bit of amplitude along the way, the frequencies, so that no one is left behind, and we get this kind of amplitude or wave of frequency f. So I hope you get that. If you face any difficulty understanding this, please inform me when we resume in the Google Meet. And here we define a very specific characteristics of a wave called bandwidth of a signal. Actually, the bandwidth of a composite signal is the difference between the highest and lowest frequencies contained in that signal. So, say for example, we have three signals, one with a frequency of 10 hertz, other with a frequency of 100 hertz, and another with a frequency of 1000 hertz. So the bandwidth here will be the difference between the highest frequency, this is the highest frequency, and this is the lowest frequency. So the bandwidth would be 1000 minus 10 hertz, or 990 hertz would be the required bandwidth. So that is what is defined in here, the bandwidth, how we define and find the bandwidth right here. It's kind of self-explanatory, and I have also discussed about it, so let's move on forward. So here we are given 5 sine waves decomposed from a composite signal of different frequencies, and we have to find the bandwidth. So as I have mentioned before, we have to find the highest bandwidth, the highest frequency, and the lowest one, find the difference between them, which will in turn give us the bandwidth. And also we have to draw a spectrum assuming all components have a maximum amplitude of 10 volt. When you are required to draw the spectrum like before, we just need to remember that we are drawing the or representing the signals in the frequency domain, and these are the values that we get after the domain. The spectrum only has 5 spikes at 100, 300, 500, 700, and 900 hertz. So that is all about it. So let's move on forward. A periodic signal has a bandwidth of 20 hertz. The highest frequency is 60 hertz. What is the lowest frequency? So here we are given the key information of bandwidth and the highest frequency of 60 hertz. We need to find the lowest frequency. So if we simplify according to algebraic rules, we can find the lowest frequency, which is 40 hertz. And during that, we needed to draw the spectrum again with all the frequencies of the which have the same amplitude. So we start from the frequency level 40 and we go through the level 60, and we draw every signal which have a value of 40 onwards up to 60, which have the same amplitude, not the different one, the same amplitude. So I think you get that. So let's move on forward. So this is the non-periodic composite signal, which has a bandwidth of 20 kilohertz with a middle frequency of 140 kilohertz and peak amplitude of 20 volt. So when we need to draw, and the two extreme frequencies have an amplitude of 0. So we need to draw the frequency domain of the signal. So when we draw this kind of frequency domain signal, at first we get the middle frequency, and we assume the highest frequency or highest amplitude is available in the middle of the frequency, middle of the bandwidth. And when we divide, because here 140 kilohertz is the middle bit of frequency, we divide the bandwidth into 200 spectrum. We plus 100 kilohertz to get that 240 kilohertz, and we minus 100 kilohertz from the left towards the left side to get this 40 kilohertz value, and we have a point of amplitude or peak amplitude of 0 at the extreme frequencies, and that is the border or the end portion of the frequencies, and that is what we are doing in here. I hope you get that. So let's move on forward. So here we have the digital signal. In addition to being represented by an analog signal, information can also be represented by a digital signal. For example, a 1 can be encoded as a positive voltage, and a 0 can as a 0 voltage or negative voltage. A digital signal can have more than 2 levels. This positive voltage level and 0 voltage level are defined as a level in the digital signal, and a digital signal can have more than these 2 levels, as we will see in a bit. In this in that case, if we represent more than one level in a digital signal, we can send more than one bit for each level. Here we see two digital signals. First, I would like to point out one is represented in a positive voltage level and 0 is represented in the 0 voltage level. So 8 bit is second is sent in 1 second, and therefore the bit rate is 8 bps, bits per second. And here 16 bits are sent in 1 second, so the bit rate is 16 bps. And we see here is that we have 4 different levels, and we can send more than one bit at a time. So for 1 that is the highest value, we send we determine it for a level 4 value, and for 10 we get the level 3. For 01 specific kind of bit string, we get the level 2, and for 00 we use the level 1. So this is how we represent two signals with 2 or more levels. I think you get that. So let's move on forward. So for this mathematical example, all you need is a calculator to calculate this kind of values. So we calculate a digital signal has 8 levels. How many bits are needed per level? So when we try to determine the level and the number of bits per level, there is a specific formula about that, which is what we are seeing here. Number of bits per level equals to log 8 to the base 2, which in terms gives us the value of 3, which is the number of bits that can be represented in in each level of 8 levels. So in 1 second we will be able to send 32 bits at a time. So we will discuss it a bit that bit later on. So here we get a digital signal has 9 levels, and how many bits we are needed for each level. So to calculate this, it is a bit tricky, because we cannot have a fraction of the bits to be sent. That is, it is not the correct answer. So we have to get a level or bit more than this. So if we have 9 levels, we have to be careful about that. The number of bits sent per level needs to be an integer as well as a power of 2. So if we want to send more than 1 bit, we need to be careful about that. We can only send a bit, 1 bit, 2 bit, 4 bit, 8 bits, etc., because it needs to be an integer and a very well known power of 2. For this example, 4 bits can be represented in one level. So we have to be clear about this incident, what is happening in here. So I hope you get that. And here is the bit rate and bit interval that we were seeing, we were talking about. A bit interval is instead of period, and bit rate instead of frequency are used to describe digital signals. So bit interval is kind of equivalent to period in the analog signal, and bit rate is kind of frequency, is similar to frequency in the analog signal, and these are described to represent digital signals. Bit interval is the time required to send one single bit, and bit rate is the number of bit intervals per second, that is usually expressed by bits per second. So these two definition is kind of important, so get note of that. So let's move forward. Now here is the mathematical example. We assume that we need to download a text document at the rate of 100 pages per second per minute. What is the required bit rate of the channel? A page is an average of 24 lines with 80 characters in each line. So for 100 pages, we get 24 lines in each page, and each 24 lines has 80 characters in each line, and one character, we assume, has 8 bits. So we need the bit rate to be at least this much to transmit it per second. For the channel to perform this exchange or to perform this data communication, so at least the channel needs to be accommodating to the speed of the bits of 1.636 megabits per second. I hope you get that. So here is the another example of similar kind of the text document, and here is the similar example for a video. I hope there is no problem about it. It would be, these two topic would be self-study for you. So if you have any problem regarding this, mention it in my next class. I hope you get that. These two informations, two examples are your self-study. And that is all for today. I hope you understand that, and I thank you all for listening with such patience. Thank you all. I hope to see you in next lecture annotation video. Have a nice day. Thank you.